When we speak of Pythagoras today, most people think of a triangle theorem they learned in school. But this reduces one of history's most enigmatic and influential thinkers to a single mathematical proof. The real Pythagoras, assuming we can know him at all, founded what was essentially a religious cult that believed numbers were divine, that souls transmigrated between bodies, and that philosophy could purify the spirit. Here lies our first challenge, one that scholars have debated for over 2,000 years. We have almost nothing written by Pythagoras himself. Every word attributed to him comes filtered through later writers, often centuries removed, many with their own agendas. Aristotle, our earliest substantial source, wrote more than 150 years after Pythagoras died, and even he speaks cautiously, saying the so-called Pythagoreans rather than Pythagoras himself. This uncertainty is not a flaw in our investigation. It is central to understanding Pythagoras. The man became a myth in his own time, and separating historical fact from legend is nearly impossible. But this very myth-making tells us something profound about how ideas gain power, how communities form around charismatic figures, and how intellectual movements evolve beyond their founders. What we can say with reasonable confidence is this. Around 570 BCE, a man named Pythagoras was born on the Greek island of Samos. He later migrated to Croton, a Greek colony in southern Italy, where he established a community that was simultaneously a school, a religious order, and a political faction. This community, the Pythagoreans, would influence Western thought for millennia, shaping mathematics, music theory, astronomy, philosophy, and even politics in ways that still echo today. Part 1. The Man Behind the Myth. Let us begin with what the ancient sources tell us about Pythagoras the person, while remaining critically aware that biography and legend have thoroughly merged. According to later accounts, Pythagoras travelled extensively before founding his school. The stories say he studied in Egypt, learning from priests who possessed ancient wisdom. Some sources claim he journeyed to Babylon, absorbing mathematical and astronomical knowledge from Chaldean scholars. A few extreme accounts even place him in India, learning from Brahmins. Modern scholars view these travel narratives with deep skepticism. They may reflect actual journeys, or they may be later inventions designed to give Pythagoras the authority of exotic wisdom. Ancient Greeks often attributed Eastern origins to philosophical ideas, believing that wisdom flowed from the ancient civilizations of Egypt and Mesopotamia to the younger Greek world. By claiming Pythagoras studied in Egypt, his followers elevated his status, making him a conduit for timeless knowledge rather than a mere innovator. What matters more than where Pythagoras travelled is what kind of community he created when he settled in Croton around 530 BCE. This was no ordinary philosophical school like those that would later emerge in Athens. It was a tightly organized society with strict rules governing every aspect of life. The Pythagorean community had initiates and full members. New members underwent years of silence, literally not speaking, while they listened to teachings from behind a curtain without seeing the master himself. This practice, called acousmaticism, from the Greek word meaning things heard, reveals something crucial about how Pythagoras operated. Authority came from his person, his voice, his presence. His followers would justify their beliefs by saying he himself said it, using he himself almost like a title. The community lived communally, sharing property. They followed elaborate dietary restrictions, most famously avoiding beans, though scholars still debate why. Some ancient sources say Pythagoras believed beans contained souls of the dead. Others claim beans cause flatulence that disturb meditation. Still others suggest the bean prohibition was political, since beans were used in voting, and Pythagoras wanted his followers separate from normal political processes. These rules were not arbitrary taboos, but flowed from Pythagoras' central teaching that life should purify the soul. This concept represented something genuinely new in Greek thought. Before Pythagoras, Greek religion focused on maintaining good relationships with the gods through proper rituals and sacrifices. Pythagoras introduced the idea that individual souls needed purification, that they could be corrupted or refined through how one lived. This brings us to one of Pythagoras' most distinctive and historically influential ideas, the transmigration of souls, or metempsychosis. Pythagoras taught that the soul was immortal and reincarnated repeatedly in different bodies, both human and animal. There is a famous story, perhaps apocryphal but revealing, about Pythagoras stopping someone from beating a dog. He claimed he recognized in the dog's yelp the voice of a deceased friend whose soul now inhabited the animal. This belief in transmigration connected to his vegetarianism, which was not based on modern concerns about animal welfare, but on religious principle. If souls migrate between species, eating meat might mean consuming someone's ancestor or future incarnation. The goal of the Pythagorean way of life was to break this cycle of rebirth, achieving a state where the soul no longer needed to return to earthly existence. Now, here is where we must confront scholarly controversy that has divided experts for generations. Did Pythagoras develop these ideas himself, or did he borrow them from other traditions? The concept of transmigration appears in Indian religions, in the Upanishads that were developing around the same time Pythagoras lived. Some scholars argue for direct influence, perhaps through Persian intermediaries. Others insist Pythagoras developed these ideas independently, noting that similar concepts about souls and purification appear in Greek Orphic religion, which predates Pythagoras. The classicist Walter Burkert, in his influential study Law and Science in Ancient Pythagoreanism, argued persuasively that we should stop trying to isolate original sources and instead see Pythagoras as synthesizing multiple strands of Greek and possibly Near Eastern thought into a new system. What made Pythagoras distinctive was not necessarily inventing new ideas, but combining them, religious practice with mathematical investigation, mysticism with rational inquiry, personal purification with communal living. The political dimension of the Pythagorean community cannot be ignored. In Crotone and other southern Italian cities, Pythagoreans gained significant political power, typically supporting aristocratic factions against democratic movements. This eventually led to violent backlash. Around 500 BCE, democratic forces attacked Pythagorean meeting houses across southern Italy, killing many members. Whether Pythagoras himself died in these attacks or had already passed away remains unclear. This political activity raises important questions about how philosophy relates to power. The Pythagoreans believed that only those who had purified their souls through study and discipline should govern. They saw democracy as rule, by the unenlightened many over the enlightened few. This elitism would echo through Western philosophy, from Plato's philosopher kings to modern technocracy. But we must also acknowledge what remains unknowable about Pythagoras himself. Did he actually make any mathematical discoveries, or did his followers attribute their own work to him? Did he write anything, or was his teaching purely oral? Was he a genuine philosopher searching for truth, or a charismatic cult leader who manipulated followers? The evidence suggests he was some complex combination of all these things. Ancient testimony consistently portrays him as extraordinarily charismatic, even magical. Stories claim he could be in two places at once, that he had a golden thigh, that a river greeted him by name. These legends reveal how completely his personality dominated his movement. This personality-driven nature would create lasting problems for Pythagoreanism. After his death, the movement fractured into competing interpretations. Some Pythagoreans, called acousmatics, focused on maintaining the exact practices and sayings of the master. Others, called mathematicians, emphasized mathematical and scientific inquiry. This split between religious practice and rational investigation, between faith and reason, would haunt Western thought for centuries. Understanding Pythagoras. The man, or at least the legendary figure, is essential because his ideas cannot be separated from the community and practices designed to realize them. The Pythagorean theorem, as we will explore, was not just an abstract mathematical truth, but part of a religious vision of cosmic order. Numbers were not mere tools for calculation, but divine entities that revealed the structure of reality itself. Part 2. Number as Reality. To understand Pythagorean philosophy, we must grasp something that sounds absurd to modern ears. The Pythagoreans did not believe numbers were useful tools for describing reality. They believed numbers were reality itself. This claim that the fundamental substance of the universe is numerical represents one of the most radical metaphysical proposals in Western philosophy. Aristotle, our primary source for this doctrine, struggled to make sense of it. In his Metaphysics, he writes that the Pythagoreans believed the elements of numbers are the elements of all things, and the whole heaven is a musical scale and a number. But Aristotle himself admits confusion about what exactly this means. Are physical objects made of numbers the way a house is made of bricks? Or do numbers somehow structure matter without being matter themselves? The evidence suggests Pythagoreans meant something more literal than mere mathematical relationships. They apparently associated specific numbers with specific things in reality. One represented the point, the origin of all things. 2 represented the line, the first extension into dimension. 3 represented the surface or plane. 4 represented the solid, three-dimensional reality. These were not metaphors. The Pythagoreans believed that when you perceived a solid object, you were genuinely encountering the number 4 manifested. They associated numbers with abstract qualities too. Justice was 4 because it represented equality, a number multiplied by itself. Marriage was 5, the union of the first even number, 2, feminine, and the first odd number after 1, 3, masculine. 7 was the virgin goddess Athena because it was the only number within 10 that neither generates another number through multiplication within the decade, nor is generated by others. To modern minds, this seems like mystical nonsense, arbitrary associations with no explanatory power. But we must understand what problem the Pythagoreans were trying to solve. The problem of change and permanence that obsessed early Greek philosophy. Earlier thinkers like Heraclitus argued that everything flows, nothing remains stable. Others like Parmenides insisted that change is impossible, that reality is one unchanging thing, and change is mere illusion. The Pythagoreans offered a middle path. Physical objects change, decay, and die, but the numerical relationships that structure them are eternal. The bronze statue can be melted down, but the ratios that defined its proportions remain true forever. This insight that mathematics describes permanent truths underlying temporary physical manifestations was genuinely revolutionary. It would eventually lead to the entire scientific project of finding mathematical laws governing nature. But the Pythagoreans went further than we do today. They did not just believe mathematics describes nature, they believed mathematics is nature, that numerical relationships do not merely characterize reality, but constitute it. Consider their most famous discovery, the mathematical ratios underlying musical harmony. When you pluck a string, it produces a note. When you pluck a string exactly half as long with the same tension, it produces a note 1 octave higher. A string 2/3 the length produces the interval called a fifth. 3/4 produces a fourth. These simple numerical ratios, 1 to 2, 2 to 3, 3 to 4, produce what we experience as beautiful harmonious sound. The Pythagoreans found this staggering. Beauty, something subjective and aesthetic, obeyed precise mathematical rules. This suggested that numbers govern not just quantity but quality, not just how many, but how things felt and appeared. They extended this insight cosmically. If simple ratios create harmony in music, perhaps the entire universe is organized according to numerical harmony. The distances between celestial bodies they proposed followed the same ratios as musical intervals. The planets in their orbits created a cosmic music, the harmony of the spheres, inaudible to human ears, corrupted by earthly existence, but perceptible to purified souls. Here we see how Pythagorean mathematics served religious purposes. Understanding numerical relationships was not merely intellectual curiosity, but spiritual practice. By grasping the numerical structure of reality, the soul aligned itself with cosmic order, purifying itself for eventual liberation from the cycle of rebirth. The number 10 held special significance, considered perfect and sacred. The Pythagoreans represented 10 through the tetractys, a triangular arrangement of dots. 1 dot at the top, 2 dots in the second row, 3 in the third, 4 in the fourth, totaling 10. This figure supposedly contained the secrets of the universe. Pythagoreans swore oaths by the tetractys, treating it as a holy symbol. Why 10? The tetractys visually demonstrates how the first 4 numbers, 1 through 4, contain and generate all others. Add them together and you get 10, which the Greeks saw as completion, after which numbers simply repeat, with 11 being 10 and 1, 12 being 10 and 2, and so forth. The tetractys also shows how geometric forms emerge from numbers. the triangle from arranging units in space. But this numerical mysticism ran into immediate problems that would eventually undermine the entire Pythagorean worldview. If everything is number, and number means positive integers and their ratios, then everything should be expressible as whole numbers or fractions. The Pythagoreans believed this with religious fervour. Reality could not contain anything that violated numerical rationality. Then came the catastrophe. One of the Pythagoreans, possibly a man named Hippasus, proved that the diagonal of a square cannot be expressed as a ratio of whole numbers. If you have a square with sides of length 1, the diagonal has length equal to what we call the square root of 2, approximately 1.414, but the precise value cannot be written as any fraction. It is what we now call an irrational number. For the Pythagoreans, this was not just a mathematical inconvenience, but a theological crisis. If irrational magnitudes exist, then number does not completely govern reality. There are lengths, real geometric facts, that escape numerical description using integers and ratios. Legend says the Pythagoreans tried to suppress this discovery. Some accounts claim Hippasus was drowned at sea for revealing the secret, either murdered by fellow Pythagoreans or punished by the gods. While this dramatic story is probably false, it captures something true about how threatening irrational numbers were to Pythagorean doctrine. Modern scholars debate how the Pythagoreans handled this crisis. Philosopher and historian of mathematics Arpad Szabo argued they essentially abandoned the idea that all magnitudes are commensurable, meaning measurable, by the same unit. Instead, they distinguished between arithmetic, dealing with discrete numbers, and geometry, dealing with continuous magnitudes. This split would have profound consequences for Greek mathematics, leading them to develop geometry far beyond arithmetic. But the deeper philosophical question remains: can reality be fundamentally mathematical if irrational numbers exist? The modern answer is yes. We simply need to expand our concept of number beyond ratios of integers. But this answer was not available to the Pythagoreans, who lacked our developed concept of real numbers. For them, the discovery of incommensurability revealed that mathematical relationships, while pervasive and important, might not be absolutely fundamental after all. Aristotle, critiquing Pythagoreanism decades later, identified additional problems with making numbers the substance of reality. Numbers are abstract, he argued, while physical objects are concrete, material, located in space and time. How can something abstract compose something concrete? It is like saying poems are made of metaphors rather than words, confusing a description with the thing itself. Furthermore, numbers are infinite, but the physical world seems finite. If numbers are the substance of things, why do we not encounter objects corresponding to every number? Where is the thing that is 1017 or 42,300,000? Yet, despite these philosophical problems, the Pythagorean intuition that reality has a mathematical structure proved extraordinarily fruitful. Galileo would later write that the book of nature is written in the language of mathematics. Modern physics describes the universe through mathematical equations, quantum mechanics through abstract Hilbert spaces, general relativity through tensor calculus. We no longer believe numbers are the substance of reality, but we do believe mathematical relationships reveal deep truths about how reality operates. The physicist Eugene Wigner wrote a famous paper titled The Unreasonable Effectiveness of Mathematics in the Natural Sciences, expressing puzzlement about why abstract mathematical structures invented by human minds correspond so precisely to physical reality. This is essentially the Pythagorean insight, restated with modern sophistication. We still do not fully understand why mathematics works so well for describing nature. Some contemporary philosophers and physicists have revived Pythagorean-style claims. Max Tegmark, a cosmologist, argues for what he calls the mathematical universe hypothesis, proposing that physical reality is not merely described by mathematics, but is mathematics, a mathematical structure. This is Pythagoreanism, updated with modern mathematical concepts, and it faces many of the same philosophical challenges Aristotle identified 2,400 years ago. The Pythagorean doctrine of number as reality also influenced Western mysticism and esotericism profoundly. Medieval Christian theologians found Pythagorean numerology compatible with biblical interpretation, finding sacred meanings in numbers throughout Scripture. Renaissance Neoplatonism revived Pythagorean themes, seeing mathematical harmony as revealing divine order. Even today, popular numerology and sacred geometry draw on garbled versions of Pythagorean ideas. We must distinguish between the genuine philosophical insight that mathematics reveals important truths about reality and the pseudoscientific claim that arbitrary numerical associations carry mystical significance. The Pythagoreans mix both together, and Western thought has struggled to separate them ever since. What remains valuable from Pythagorean metaphysics is the recognition that abstract patterns and relationships have a kind of reality independent of particular physical instantiations. The ratio 1:2 exists independently of any particular string or pair of objects that exemplifies it. Mathematical truths seem to have a necessity and permanence that physical truths lack. Water boils at 100 degrees Celsius contingently because of particular physical laws, but the ratio of a circle's circumference to its diameter is pi necessarily in all possible worlds. Whether this means numbers are more real than physical objects, or merely that we are confused about what reality means, remains debated. But the Pythagoreans forced us to ask the question, and Western philosophy has never stopped trying to answer it. Part 3. Mathematical Discoveries and the Famous Theorem. When we speak of the Pythagorean theorem, we immediately confront a problem of attribution that exemplifies the broader difficulty of identifying what Pythagoras himself contributed versus what his followers developed over centuries. The theorem states that in a right triangle, the square built on the hypotenuse equals the sum of the squares built on the other two sides. In modern notation, we write it compactly, but following our rules, we must say it in words. If a right triangle has legs of lengths A and B, and hypotenuse of length C, then the square of C equals the square of A plus the square of B. Here is what we know with certainty. This relationship was known to Babylonian mathematicians roughly 1,000 years before Pythagoras was born. Clay tablets from ancient Mesopotamia contain problems that clearly demonstrate knowledge of this relationship. The famous Plimpton 322 tablet, dating to around 1800 BCE, lists Pythagorean triples, sets of three whole numbers that satisfy the relationship. So Pythagoras did not discover the theorem. What then did he or his school contribute? The most defensible claim is that the Pythagoreans provided the first rigorous proof, transforming an empirical observation used by surveyors and architects into a demonstrated mathematical truth. But even this claim is uncertain. We have no Pythagorean texts proving the theorem. The Greek mathematician Euclid, writing around 300 BCE, presents a proof in his Elements, but he lived 200 years after Pythagoras and does not attribute it to him. Later, ancient commentators claim Pythagoras proved the theorem, but they write hundreds of years after the fact with no direct evidence. The historian of mathematics Bartel van der Waerden argued that the Pythagoreans likely developed geometric proof techniques precisely through working on this theorem. The conceptual leap from knowing that a relationship holds in many cases to proving it must hold in all cases represents the birth of deductive mathematics. If the Pythagoreans made this leap, it would justify crediting them with the theorem even if Pythagoras personally had nothing to do with it. Walter Burkert, in his skeptical analysis, went further. He argued that we cannot confidently attribute any specific mathematical proof to the early Pythagoreans at all. The association between Pythagoreanism and mathematics may have been exaggerated by later writers like Aristotle and Plato, who admired mathematical reasoning and wanted to connect it to the prestigious Pythagorean name. This scholarly debate matters because it reveals how intellectual history gets constructed and mythologized. The theorem now bears Pythagoras' name, taught to millions of students worldwide, yet the historical Pythagoras may never have thought about it. The naming reflects not historical fact, but the power of the Pythagorean legend. Setting aside attribution, let us explore what the theorem actually means and why it matters. At first glance, it appears to be merely a practical tool for surveyors and builders to calculate distances. But the theorem connects geometry and arithmetic in profound ways, revealing deep structural relationships in space itself. Consider what it means to square a number. Geometrically, squaring means constructing an actual square with that number as the side length. A 3 by 3 square contains 9 unit squares within it, so 3 squared equals 9. The theorem says that if you build squares on all 3 sides of a right triangle, the area of the largest square exactly equals the combined areas of the 2 smaller squares. This is not obvious, and not something you would expect without proof. Why should areas relate this way? What is special about right triangles that makes this work? The theorem reveals hidden order in space, the kind of mathematical harmony the Pythagoreans believed governed reality. Ancient proofs of the theorem used geometric dissection, cutting and rearranging shapes to show equality of areas. The Chinese mathematical text Zhou Bisuan Jing, roughly contemporary with Pythagoras, contains a beautiful proof using this method. You draw the 2 smaller squares and show how they can be cut and reassembled to exactly fill the larger square. This visual demonstration makes the theorem tangible, showing that the relationship is not numerical coincidence, but geometric necessity. The theorem also generates an infinite family of right triangles with whole number sides, called Pythagorean triples. The most famous is 3, 4, 5, where 3 squared, 9, plus 4 squared, 16, equals 5 squared, 25. Others include 5, 12, 13, and 8, 15, 17. Ancient builders used the 3-4-5 triangle to construct right angles, stretching a rope with 12 equally spaced knots into this triangle to guarantee a perfect right angle. But the theorem also led directly to the crisis we mentioned earlier, the discovery of irrational numbers. Apply the theorem to the simplest possible right triangle, a right isosceles triangle with both legs equal to 1. The hypotenuse squared must equal 1 squared plus 1 squared, which equals 2. Therefore, the hypotenuse equals the square root of 2. The proof that the square root of 2 cannot equal any fraction of whole numbers uses beautiful logical reasoning that may well have come from the Pythagorean school. Assume it could be written as a fraction in lowest terms, meaning the numerator and denominator share no common factors. Through algebraic manipulation, which I will describe in words rather than symbols, you can show that both numerator and denominator must be even numbers, meaning they share the common factor of 2. But this contradicts our assumption that the fraction was in lowest terms. Therefore, our initial assumption was wrong, and the square root of 2 cannot be expressed as any fraction. This proof exemplifies proof by contradiction, showing something is impossible by demonstrating that assuming it leads to logical absurdity. This technique, called reductio ad absurdum in Latin, became fundamental to mathematical reasoning. If the Pythagoreans developed it, they contributed something far more important than any single theorem, a method for establishing mathematical truth. The psychological impact of discovering irrational numbers deserves emphasis. Imagine believing with religious conviction that reality is fundamentally rational, composed of whole numbers and their ratios, only to prove rigorously that some geometric magnitudes escape this rationality. It is as if a Christian theologian proved logically that God does not exist, or a physicist demonstrated that physical law breaks down randomly. The entire worldview collapses. How did Pythagorean mathematics develop after this crisis? The evidence suggests they increasingly separated arithmetic, the study of discrete numbers, from geometry, the study of continuous magnitude. Greek mathematics, after the 5th century BCE, focuses heavily on geometry while making less progress in what we would call algebra or number theory. This may reflect the Pythagorean trauma, avoiding arithmetic questions that might generate more irrational contradictions. Beyond the famous theorem, what other mathematics can we attribute to the Pythagorean school? They certainly studied figurate numbers, numbers that can be arranged into regular geometric shapes. Triangular numbers like 3, 6, 10, 15 can be arranged in triangular patterns. Square numbers like 4, 9, 16 obviously form squares. The Pythagoreans investigated relationships between these figurate numbers, discovering, for instance, that any square number equals the sum of 2 consecutive triangular numbers. They also studied perfect numbers, numbers that equal the sum of their proper divisors. 6 is perfect because its divisors 1, 2, and 3 sum to 6. 28 is perfect because 1 plus 2 plus 4 plus 7 plus 14 equals 28. Perfect numbers were seen as having special significance, reflecting cosmic harmony. Euclid later proved a formula for generating even perfect numbers, though whether this derives from Pythagorean work remains unclear. The Pythagoreans discovered that adding successive odd numbers generates square numbers. 1 equals 1 squared. 1 plus 3 equals 4, 2 squared. 1 plus 3 plus 5 equals 9, 3 squared. This delighted them because it connected odd numbers, which they considered masculine and active, to squares, which represented stability and perfection. In music theory, the Pythagoreans made genuine, lasting contributions. They were apparently the first to recognize that musical intervals correspond to precise numerical ratios. The octave is 1 to 2, the fifth is 2 to 3, the fourth is 3 to 4. These ratios, using only the first 4 numbers, reinforced their mystical reverence for the tetractys. They constructed the musical scale by stacking these intervals. Starting from a bass note, go up a fifth to reach the second note of the scale, then up a fourth from there to reach the third note, and so on. This generates what we call the Pythagorean tuning system, still used in some musical traditions today. However, Pythagorean tuning has inherent problems. Certain intervals sound dissonant because the mathematical ratios do not quite work out perfectly. This reflects another limitation of forcing reality into simple numerical relationships. In astronomy, the Pythagoreans attempted to explain planetary motion using numerical principles, which we will explore more deeply in the next section. But their mathematical contributions to astronomy proved less successful than their musical insights. They valued numerical elegance over empirical accuracy, a tendency that would plague mathematical physics until Galileo and Newton insisted on matching theory to observation. We must address one final question. Why did the theorem attributed to Pythagoras become so famous, so central to mathematics education worldwide, while other equally important results remain obscure? Part of the answer is pedagogical. The theorem is simple enough that children can understand it, but deep enough to support sophisticated proofs and applications. It bridges arithmetic and geometry, demonstrating how different mathematical domains connect. Learning the theorem and its proof teaches logical reasoning, visual thinking, and algebraic manipulation all at once. But the fame also reflects effective branding. Attaching a name to a theorem, especially a name like Pythagoras that carries mystical prestige, makes it memorable and significant seeming. Students learn the Pythagorean theorem as if learning a secret of the universe, which, in a sense, they are. The name elevates what might otherwise seem a technical result into a profound truth about reality. Mathematically, the theorem remains fundamental. It defines Euclidean distance, the basic notion of how far apart points are in space. Modern physics uses generalizations of the theorem throughout, from special relativity's space-time interval to quantum mechanics' Hilbert space geometry. The theorem's basic insight, that spatial relationships can be captured exactly through arithmetic relationships, continues to generate new mathematics and physics. Yet we must remember that theorem is only one small piece of a much larger Pythagorean vision, that mathematical relationships reveal cosmic order, and that understanding these relationships purifies the soul. The theorem was not merely technical knowledge, but spiritual knowledge. Modern education has divorced mathematical results from this metaphysical and ethical context, teaching the theorem while forgetting why it mattered to those who discovered or proved it. Whether that divorce represents progress or loss remains debatable. We gain precision and rigour by treating mathematics as pure logic, independent of metaphysics. But we may lose a sense of wonder the feeling that mathematical truth connects to deeper truths about existence, meaning, and value. The Pythagoreans would find our purely technical approach to their theorem profoundly unsatisfying, like analysing the metre of poetry while ignoring what the poem means. Part 4. The Harmony of the Spheres. Among all Pythagorean doctrines, none captures their vision more completely than the harmony of the spheres, the belief that celestial bodies produce musical sounds as they move through the heavens, and that these sounds follow the same numerical ratios that create musical harmony on Earth. This idea seems immediately absurd to modern ears. We know space contains no air, no medium to transmit sound waves. We have sent spacecraft throughout the solar system and detected no cosmic music. The harmony of the spheres appears to be pure fantasy, poetic at best, delusional at worst. But dismissing it as mere superstition misses why it was believed and what it reveals about how the Pythagoreans understood the relationship between mathematics, physics, and value. Start with their empirical discovery about music. Pluck a string, it produces a tone. Pluck a string half as long with identical tension, it produces a tone 1 octave higher. The octave, what we experience as two notes harmonizing perfectly, corresponds to the exact numerical ratio 1 to 2, the simplest ratio possible above 1 to 1. The fifth, the next most consonant interval, corresponds to the ratio 2 to 3. The fourth corresponds to 3 to 4. More complex ratios produce increasingly dissonant sounds. The Pythagoreans discovered this, according to legend, when Pythagoras himself walked past a blacksmith's shop and noticed that hammers of different weights striking anvils produced harmonious or dissonant sounds depending on their weight ratios. This story is almost certainly false. The physics does not work that way, but it reveals how the Pythagoreans thought about their discovery. They believed they had found an objective basis for aesthetic judgment. Beauty in music was not subjective preference, but mathematical fact. Certain ratios necessarily sound good to human ears because those ratios reflect fundamental cosmic order. This was revolutionary. Before this, people assumed beauty was purely in the eye or ear of the beholder. The Pythagoreans showed that, at least in music, beauty followed rules, and those rules were mathematical. This suggested beauty everywhere might have mathematical foundations. Perhaps visual beauty depended on mathematical proportions too, an idea that would influence architecture and art for millennia through concepts like the golden ratio. Having discovered that musical harmony follows mathematical ratios, the Pythagoreans made a daring generalization. If harmony on Earth is mathematical, and the cosmos is fundamentally mathematical, then the cosmos itself must be harmonious. The movements of celestial bodies, they reasoned, must follow the same ratios that create musical consonants. But why would celestial motion produce sound at all? The Pythagoreans believed that anything moving through space must displace the medium it moves through, creating vibrations we perceive as sound. The faster something moves, the higher the pitch it produces. Since planets move at different speeds and distances from Earth, they would produce different tones, and those tones would necessarily harmonize according to the same mathematical ratios that govern music. The obvious objection arises immediately. If the planets are constantly producing these sounds, why do we not hear them? The Pythagorean answer was sophisticated. We do not hear the cosmic music because we have heard it continuously since birth. Just as someone living next to a waterfall eventually stops consciously hearing the water, we are so accustomed to the harmony of the spheres that we no longer perceive it. It has become the background silence against which other sounds stand out. Some Pythagorean sources claimed that purified souls could learn to hear the cosmic music through philosophical training and spiritual practice. Others said that Pythagoras himself, being divinely gifted or having achieved complete purification, could hear what others could not. This made the doctrine unfalsifiable. Any failure to detect the music could be attributed to the listener's impurity rather than the music's absence. The philosopher Aristotle, always skeptical of Pythagorean claims, attacked the harmony of the spheres on multiple grounds. First, he pointed out that sound requires a medium, and the heavens contain no air or water to transmit vibrations. Second, he noted that the speeds and distances of planets do not actually follow simple musical ratios. The theory imposed aesthetic preferences onto reality rather than deriving from observation. Most devastatingly, Aristotle argued that if the planets generated sound through motion, the amount of sound would be tremendous given their size and speed. We should not merely hear it, we should be deafened by it. The idea that we simply do not notice because we have always heard it struck him as desperate special pleading. Yet, despite Aristotle's criticisms, the harmony of the spheres persisted for 2,000 years as both scientific hypothesis and poetic inspiration. Why did it prove so durable? The doctrine captured something psychologically deep about human desire to find meaning in the cosmos. We want the universe to be orderly rather than chaotic, beautiful rather than ugly, purposeful rather than random. The harmony of the spheres promised all three, the cosmos as a perfectly tuned instrument playing eternal music according to mathematical law. It also offered a powerful metaphor for how different levels of reality relate to each other. Musical harmony on Earth reflects cosmic harmony in the heavens, which reflects mathematical harmony in the abstract realm of numbers, which reflects divine harmony in the mind of God or the structure of ultimate reality. Everything connects in a great chain of correspondence, with mathematics providing the links. Medieval Christian theologians found the harmony of the spheres compatible with biblical creation. God created the universe through divine reason, which naturally expressed itself mathematically. The heavenly music was literally the song of creation, the word through which God spoke the cosmos into being. Boethius, writing in the 6th century CE, distinguished between musica instrumentalis, music made by instruments, musica humana, the harmony of body and soul, and musica mundana, cosmic harmony. All three followed the same mathematical principles because all three ultimately derived from divine order. The Renaissance revived Pythagorean ideas with renewed intensity. Johannes Kepler, the great astronomer who discovered that planets move in ellipses rather than circles, spent years trying to find musical ratios in planetary orbits. His book Harmonices Mundi, The Harmony of the World, published in 1619, attempted to show that the speeds of planets at different points in their orbits correspond to musical intervals. Kepler's work shows both the power and the problem of Pythagorean thinking. His commitment to finding mathematical harmony in the heavens drove him to analyze planetary data with unprecedented precision, ultimately leading to his three laws of planetary motion that would form the foundation for Newtonian physics. But his attempt to find literal musical ratios failed. The actual ratios did not produce harmonious intervals. Still, Kepler considered his harmonic discoveries his greatest achievement, more important than his laws of motion that we now recognize as his real contribution. This reveals something crucial about how science actually develops. Scientists are not purely rational calculators following evidence wherever it leads. They are driven by aesthetic preferences, metaphysical commitments, and desires for meaning that often contradict evidence. The Pythagorean vision of a mathematically harmonious cosmos inspired enormous scientific progress, even though the specific claims about cosmic music proved false. Modern physics has vindicated a weaker version of the Pythagorean intuition, while abandoning literal harmony of the spheres. The universe does follow mathematical laws with remarkable precision. Quantum mechanics describes atomic behavior through wave equations that have literal harmonic properties. Electrons in atoms occupy states characterized by harmonic frequencies. While these are not sounds we could hear, they are genuine vibrations with mathematical properties analogous to musical tones. String theory, a speculative theory attempting to unify quantum mechanics and general relativity, proposes that fundamental particles are actually tiny vibrating strings. Different vibration modes of these strings correspond to different particles, much as different vibration modes of a violin string produce different notes. This is not the harmony of the spheres, but it is a theory where vibration and mathematics remain intimately connected at the deepest level of reality. We can also interpret harmony of the spheres more abstractly, not as literal sound, but as metaphor for mathematical relationships. In this reading, the Pythagoreans were saying that celestial mechanics follows orderly mathematical principles, which is true. The harmony is not acoustic but mathematical, the way planetary orbits relate to each other through gravitational interactions that can be described with equations. But this charitable interpretation removes what made the doctrine compelling, the idea that the cosmos is not merely orderly but beautiful, that mathematical relationships carry aesthetic value. Modern physics describes the universe through equations, but claims no authority to say whether those equations are beautiful or ugly, meaningful or arbitrary. We have fact without value, mathematics divorced from aesthetics. The Pythagoreans insisted these cannot be separated. Mathematical order is beautiful, and beauty is a kind of truth. When physicists today speak of elegant equations or beautiful theories, they unconsciously echo Pythagorean assumptions, suggesting that aesthetic criteria should guide our understanding of nature. This creates a tension in contemporary physics. On one hand, scientists insist on value-free objectivity, rejecting any claim that nature cares about human aesthetic preferences. On the other hand, physicists routinely prefer simpler, more symmetric, more beautiful theories, assuming nature follows principles we find aesthetically pleasing. Is this justified, or is it anthropocentric projection? The Pythagorean harmony of the spheres was wrong as physics, but may contain a philosophical insight modern science has not fully processed. If mathematical relationships really are fundamental to nature, and if humans can perceive those relationships as beautiful, what does that say about the relationship between mind and cosmos? Are we lucky that the universe happens to be mathematically describable? Or is there a deeper reason why mathematical beauty and physical truth coincide? These questions exceed the scope of physics and enter metaphysics, precisely the territory the Pythagoreans inhabited. They believed mathematics connected human minds to cosmic order, that studying mathematical relationships was simultaneously studying nature and studying the divine. Modern science has fractured this unity, treating mathematics as a human tool, nature as indifferent matter and energy, and the divine as outside scientific inquiry entirely. Whether this fractured worldview is more true than the integrated Pythagorean vision, or simply more limited, remains an open question that scientists and philosophers continue to debate. Part 5. Pythagorean Cosmology and Astronomy. The Pythagorean model of the cosmos was radical for its time, breaking decisively with common sense and laying groundwork for future scientific revolutions. But it also exemplified how the Pythagorean obsession with numerical perfection could lead them astray, sacrificing empirical accuracy for mathematical elegance. Most ancient Greeks believed in a geocentric cosmos, with Earth stationary at the centre and celestial bodies rotating around it on crystalline spheres. This matched everyday experience. We feel no motion, and we see the sun, moon, stars and planets moving across the sky. The Earth seems obviously immobile and central. The Pythagoreans rejected this seemingly obvious truth. According to reports from Aristotle and later writers, some Pythagoreans, particularly a figure named Philolaus, who lived in the 5th century BCE, proposed that Earth moves. Not only moves, but orbits around a central fire, which they called the hearth of the universe. This central fire was not the sun. The sun, in their model, was a separate body that reflected light from the central fire. Earth orbited the central fire, always keeping the same face toward it, which explained why we never see this central fire. It remains perpetually on the opposite side of Earth from the inhabited regions. To modern readers familiar with heliocentrism, where Earth orbits the sun, this Pythagorean model seems like a confused precursor to the correct theory. But actually, the Pythagorean system was not an early version of Copernican heliocentrism, but something stranger. The central fire was not the sun, and their reasons for positing a moving Earth had nothing to do with astronomical observation and everything to do with numerology and metaphysics. The number 10 was sacred to Pythagoreans, the perfect number containing all others, represented by the holy tetractys. But when they counted the celestial bodies visible to the naked eye, they found only 9. Earth itself, the moon, the sun, Mercury, Venus, Mars, Jupiter, Saturn, and the sphere of fixed stars. This was one short of 10, an intolerable imperfection in a cosmos governed by numerical harmony. Their solution was to invent an additional body, which they called the counter-Earth, or Antichthon. This mysterious object orbited the central fire opposite Earth, explaining why we never see it. It is always hidden behind the central fire from our perspective. With the counter-Earth added, the count reached 10, the perfect number, and cosmic harmony was restored. From a modern scientific perspective, this is absurd reasoning. They invented celestial bodies not because observation demanded them, but because their numerological system required them. This is exactly backwards. Observation should drive theory, not the other way around. Yet we must appreciate the genuine conceptual breakthrough buried in this mystical packaging. The Pythagoreans dared to question the self-evident truth that Earth is stationary and central. They proposed that human perception could be systematically wrong about basic facts of cosmic structure. This was revolutionary skepticism about the reliability of immediate experience. Why might Earth move without us feeling it? The Pythagoreans apparently reasoned that if motion is smooth and constant, we would not perceive it directly. Just as passengers on a smoothly sailing ship do not feel the ship's motion, inhabitants of Earth would not feel its orbit. This anticipates the principle of inertia that Galileo would articulate 2,000 years later, that uniform motion is indistinguishable from rest without external reference points. They also understood that the apparent motion of celestial bodies across the sky could be explained either by those bodies moving around a stationary Earth or by Earth rotating while those bodies remain relatively fixed. These explanations are mathematically equivalent in terms of describing the observed phenomena. Choosing between them requires additional criteria beyond mere observation. Criteria like simplicity, elegance, or, in the Pythagorean case, numerical perfection. Aristotle criticized the Pythagorean cosmology mercilessly. He pointed out that postulating invisible bodies just to reach a numerologically significant count violates basic principles of scientific reasoning. He also argued that their central fire makes no physical sense. We should see its light reflected off the moon during certain parts of the lunar cycle, but we do not. The model failed to match observational evidence. Yet Aristotle recognized what was valuable in Pythagorean astronomy. They emphasized mathematical relationships between celestial phenomena. They sought quantitative ratios for planetary distances and orbital periods, even if the ratios they proposed were wrong. This commitment to mathematical description of nature would eventually prove essential to scientific progress. Later, Pythagoreans modified the cosmology in various ways. Some abandoned the central fire and counter-Earth, instead proposing that Earth rotates on its axis daily, which more simply explains the apparent rotation of the stars. Heraclides of Pontus, a 4th century BCE astronomer influenced by Pythagoreanism, proposed that Mercury and Venus orbit the Sun while the Sun orbits Earth, a hybrid model that matched observations better than simple geocentrism. Most dramatically, Aristarchus of Samos proposed in the 3rd century BCE a fully heliocentric model with Earth and planets orbiting the Sun. Aristarchus was not explicitly a Pythagorean, but his willingness to challenge geocentric orthodoxy likely drew on the Pythagorean tradition of questioning common sense for mathematical reasons. However, Aristarchus's heliocentric theory was rejected by ancient astronomers because it seemed to contradict observation. If Earth moves around the Sun, we should see stellar parallax, the apparent shift in star positions as Earth changes its viewpoint. Since no parallax was detected, astronomers concluded Earth must be stationary. We now know stellar parallax exists, but was too small to detect without telescopes because stars are vastly farther away than ancient astronomers imagined. Aristarchus was right, but could not prove it with available technology. His heliocentric theory was forgotten, and astronomy reverted to increasingly complex geocentric models that added epicycles and deference to match observations while keeping Earth central and stationary. When Copernicus revived heliocentrism in the 16th century, he explicitly invoked Pythagorean and Platonic precedents, framing his theory not as innovation, but as recovering ancient wisdom. This rhetorical strategy helped legitimate a theory that seemed to contradict common sense and scripture. By claiming Pythagorean authority, Copernicus suggested that heliocentrism was not dangerous novelty, but rediscovery of forgotten truth. Kepler, as we mentioned, was even more explicitly Pythagorean in his astronomical work. His attempt to find musical ratios in planetary orbits failed, but his conviction that God designed the cosmos according to mathematical harmonies drove him to discover his 3 laws of planetary motion. The first law, that planets move in ellipses with the Sun at one focus, finally abandoned the ancient assumption that celestial motion must be circular, an assumption rooted in the Pythagorean belief that circles are perfect and therefore appropriate for the perfect heavens. This reveals an important lesson about the relationship between metaphysical assumptions and scientific progress. The Pythagorean commitment to mathematical cosmic order was partially correct and profoundly productive, inspiring centuries of astronomical investigation. But specific Pythagorean assumptions, like the perfection of circular motion and the sacredness of the number 10, turned out to be wrong and had to be abandoned. Science advances not by rejecting metaphysics entirely, but by testing and refining metaphysical assumptions against evidence. The Pythagoreans taught us to look for mathematical patterns in nature, which was correct. But they also taught us that these patterns must match specific numbers they considered sacred, which was wrong. Later, scientists kept the first lesson and discarded the second. Contemporary cosmology still grapples with the tension between mathematical elegance and empirical adequacy. String theorists propose 10 dimensions, not because observation requires them, but because the mathematics works out most elegantly in 10 dimensions. Is this Pythagorean numerology reborn, or is it legitimate theoretical physics? The debate continues, with critics accusing string theory of being unfalsifiable mathematical speculation, while defenders argue that mathematical elegance has historically guided us toward truth. The Pythagorean astronomical legacy is thus deeply ambivalent. They pioneered the idea that Earth might move, that mathematical relationships govern celestial phenomena, and that observation can mislead us about fundamental cosmic structure. These insights were genuinely revolutionary, but they also subordinated observation to numerological prejudice, inventing counter-Earths and central fires to satisfy mystical requirements rather than to explain phenomena. Modern astronomy has learned to be Pythagorean in its mathematical approach, but anti-Pythagorean in its empirical discipline. We seek mathematical laws, but insist those laws match observation, no matter how inelegant or counterintuitive the results. When quantum mechanics emerged with its strange, probabilistic character and wave-particle duality, physicists accepted it despite its ugliness, because experiment demanded it. A Pythagorean might have rejected quantum mechanics for violating classical mathematical elegance, and would have been wrong. Yet perhaps physics has overcorrected away from Pythagorean aesthetics. When multiple theories equally match current data, should we prefer simpler, more elegant theories? If so, we are making a Pythagorean assumption that nature prefers mathematical beauty. If not, we may miss deep truths by treating all empirically adequate theories as equally good. The Pythagorean astronomers force us to confront questions about scientific methodology that remain unresolved. How should aesthetic criteria like elegance, simplicity and symmetry influence theory choice? When should we trust mathematical beauty over empirical observation? And when should we do the opposite? These are not merely historical questions, but live issues in contemporary physics and cosmology. Part 6. The Soul, Knowledge and Purification. Pythagorean epistemology, their theory of knowledge, cannot be separated from their religious views about the soul. For them, learning was not merely accumulating information, but purifying the soul, and the highest knowledge was not about external facts, but about the soul's own nature and destiny. Start with the Pythagorean doctrine of the soul we mentioned earlier, metempsychosis or transmigration. The soul is immortal and reincarnates repeatedly in different bodies, both human and animal. Between incarnations, the soul exists in a pure state, possessing knowledge of eternal truths. Birth into a physical body causes the soul to forget this knowledge, trapped in ignorance by the limitations and distractions of material existence. This created a problem that Plato would later develop extensively. How can we learn anything genuinely new if learning means recovering knowledge we have forgotten? The Pythagorean answer was that all learning is actually recollection, called anamnesis in Greek. When we grasp a mathematical truth or philosophical insight, we are not discovering something external, but remembering what our soul knew before birth. Consider how this applies to mathematics. When you understand that the square root of 2 is irrational, you have proven something necessarily true about numbers. This truth did not begin to be true when you proved it, nor will it cease being true if you forget the proof. Mathematical truths seem to exist independently of anyone thinking about them, eternal and unchanging. The Pythagoreans concluded that mathematical knowledge must come from a part of us that is itself eternal and unchanging, namely the soul. The soul grasps mathematical truths because it shares their eternal nature. Physical senses cannot perceive eternal truths, only temporary particular things. Therefore, mathematical knowledge must come from the soul, accessing a reality beyond the physical world. This epistemology has profound ethical implications. If the soul is divine and eternal, but trapped in a corruptible body, philosophy becomes the practice of liberating the soul from bodily entanglement. The Pythagorean way of life, with its dietary restrictions, ritual practices and mathematical studies, aimed at purifying the soul so it could escape the cycle of reincarnation and return to its divine origin. Mathematics played a special role in this purification. Studying mathematics trains the soul to focus on eternal, immaterial realities rather than temporary physical appearances. It develops the soul's capacity for abstract thought, strengthening its divine aspect while weakening attachment to bodily concerns. Mathematical knowledge is thus not merely theoretical, but transformative, changing the knower's very nature. This helps explain why the Pythagoreans surrounded mathematics with religious ritual and secrecy. Mathematical knowledge was sacred wisdom, not to be shared with the unpurified. Revealing it to those unprepared could be spiritually dangerous, like giving a child fire or a weapon. The initiate needed proper moral and spiritual preparation before receiving mathematical teaching. Scholars debate how much of this epistemology actually comes from Pythagoras himself versus later elaboration by Plato and Neo-Platonists. The theory of recollection appears most fully developed in Plato's dialogue Meno, written 150 years after Pythagoras. Plato clearly drew on Pythagorean ideas, but also developed them in his own distinctive ways. Separating Pythagorean from Platonic epistemology is nearly impossible, given our sources. What we can say is that the Pythagorean Platonic epistemology dominated Western philosophy for over 2,000 years. The idea that genuine knowledge concerns eternal truths accessible to pure reason rather than temporary facts perceived by unreliable senses shaped medieval Christian philosophy, Renaissance thought, and Enlightenment rationalism. Only in the modern era has empiricism, the view that knowledge comes from sensory experience, seriously challenged this rationalist tradition. The Pythagorean view faces serious philosophical objections. If learning is recollection of prenatal knowledge, how did the soul acquire that knowledge originally? Did it exist eternally, already knowing everything, or was there a first time it learned? Either answer creates problems. If the soul always already knew everything, why does it forget upon birth? And why do some souls seem to recollect more easily than others? If the soul once learned for the first time, then learning cannot always be recollection, and we need a different epistemology for that original learning. Furthermore, the doctrine of recollection seems to conflict with the obvious fact that we do learn new things. When Pythagoras or his followers discovered that the square root of 2 is irrational, were they recollecting prenatal knowledge, or were they making a genuine discovery? If recollecting, why did it take until the 5th century BCE for any soul to recollect this particular truth? The recollection theory struggles to explain historical progress in knowledge. Modern cognitive science has demolished the metaphysical framework behind Pythagorean epistemology. We know that brains, not immaterial souls, process information. We understand learning as the formation of new neural connections, not the recall of eternal truths. Mathematical knowledge emerges from pattern recognition and symbolic manipulation, not from the soul accessing a transcendent realm. Yet something puzzling remains. Mathematical truths do seem to have a kind of necessity and objectivity that empirical facts lack. That 7 plus 5 equals 12 is true in a different way than that water freezes at 0 degrees Celsius. The latter depends on contingent physical laws that might have been different, while the former seems necessarily true in all possible worlds. Contemporary philosophy of mathematics still debates whether mathematical objects like numbers exist independently of human minds, a position called Platonism, or whether they are human constructions, nominalism. The Platonist position is essentially the Pythagorean view, updated for modern thought. Mathematics describes an objective realm of abstract entities that we discover rather than invent. The philosopher Kurt Gödel, famous for his incompleteness theorems that showed inherent limitations in formal mathematical systems, defended mathematical Platonism. He argued that mathematical intuition gives us access to mathematical facts independently of formal proof, much as sensory perception gives us access to physical facts. This mathematical intuition, Gödel suggested, functions analogously to how the Pythagoreans conceived the soul's direct apprehension of eternal truths. Critics respond that mathematical Platonism is mysticism dressed in philosophical language. How could an immaterial mind interact with abstract mathematical objects? If mathematical truths exist outside space and time, causally disconnected from physical reality, how can we have any knowledge of them? The epistemological problem seems insurmountable. Yet nominalism, the alternative view that mathematical objects are mere constructions or linguistic conventions, faces its own problems. If mathematics is just a game we invented, why does it describe physical reality so accurately? How could a human invention predict the behavior of subatomic particles or distant galaxies? The effectiveness of mathematics in science suggests it captures something objectively real about nature, not merely human convention. We might interpret Pythagorean epistemology more charitably by separating its psychological and metaphysical claims. Perhaps the Pythagoreans were wrong about immaterial souls and reincarnation, but right that mathematical knowledge involves a distinctive cognitive process different from empirical observation. When we grasp a mathematical proof, we achieve a kind of certainty unavailable in empirical science. We see not just that something is true, but why it must be true. This phenomenology of mathematical understanding, the experience of seeing necessity in mathematical relationships, is what the Pythagoreans tried to capture with their doctrine of recollection. They lacked modern concepts like innate cognitive structures or evolved pattern recognition capacities, so they explained this feeling of necessity through the soul's prenatal knowledge. We can reject their metaphysics while acknowledging they identified something genuine about mathematical cognition. The Pythagorean connection between knowledge and purification also deserves reconsideration. We moderns separate intellectual and ethical development, treating knowledge acquisition as value-neutral technical training. The Pythagoreans insisted these cannot be separated, that how we live affects what we can know, and what we know should transform how we live. Contemporary virtue epistemology, a movement in philosophy that emphasizes intellectual virtues like open-mindedness, intellectual courage, and epistemic humility, echoes Pythagorean themes. It suggests that becoming a good knower requires developing good intellectual character, not merely mastering technical skills. Mathematical understanding, from this perspective, requires cultivating attention, precision, and honesty about what we do and do not grasp. The Pythagorean practice of periods of silence for initiates also resonates with contemporary emphasis on contemplative practices in education. Before speaking, one must learn to listen deeply. Before asserting your own views, you must genuinely understand others' perspectives. This pedagogical wisdom transcends Pythagorean metaphysics. Finally, the Pythagorean idea that knowledge is ultimately self-knowledge, that studying mathematics and nature ultimately reveals truths about the soul studying them, anticipates developments in modern physics and cognitive science. Quantum mechanics suggests that observation affects what is observed, collapsing the observer-observed distinction. Neuroscience studies how brains construct models of reality, blurring the line between what is known and who does the knowing. The Pythagorean insight that knowledge always involves the knower as much as the known remains relevant. Part 7. The Pythagorean Way of Life. Philosophy for the Pythagoreans was not an academic discipline but a complete way of life, encompassing diet, dress, speech, daily rituals, and social relationships. This integration of intellectual inquiry with practical living distinguish Pythagoreanism from most ancient philosophical schools and gives it continued relevance for anyone seeking to live philosophically. The Pythagorean community at Croton functioned as what we might call a commune or intentional community. Members surrendered personal property to common ownership, lived together in shared housing, and followed a rigorous daily schedule of activities. This communal structure was not merely practical, but reflected their metaphysical commitments. If individual souls are all fragments of the same divine reality, temporarily separated by bodily incarnation, then private property and individualistic living contradict ultimate truth. The daily routine began at dawn with musical and mathematical exercises. Members would sing hymns and practice playing the lyre, training both voice and mind in harmonic relationships. This was not entertainment, but spiritual practice, attuning the soul to cosmic harmonies. Mathematical study followed, not as abstract calculation, but as meditation on eternal truths. Physical exercise came next, but not competitive athletics for individual glory. The Pythagoreans preferred walking, dancing, and activities that promoted health without encouraging vanity or aggression. The body was a temple for the soul, to be maintained but not obsessed over. The goal was balance, developing bodily health to support intellectual and spiritual pursuits without letting physical concerns dominate. Midday brought communal meals with strict dietary rules. The most famous prohibition was against eating beans, but Pythagoreans also avoided meat, though sources disagree about how strictly. Some accounts suggest they ate fish, but not land animals, others that they practiced complete vegetarianism. The reasoning combined religious, philosophical, and perhaps practical concerns. Since souls transmigrate between species, eating animal flesh might mean consuming a relative or friend whose soul now inhabited that animal. This made meat-eating morally problematic, potentially a kind of cannibalism. But the prohibition also reflected their view of the body as needing purification. Heavy foods like meat weighed down the soul, making philosophical concentration difficult. Light foods like vegetables and grains kept the body nourished without dulling mental faculties. The bean taboo has puzzled scholars for centuries. Ancient sources offer multiple explanations, none entirely satisfactory. Some say beans resemble human fetuses or testicles in shape, making them symbolically problematic. Others claim beans cause flatulence that disturbs meditative practice. Still others suggest beans were used in Athenian voting, one bean colour for yes, another for no, and Pythagoreans wanted to separate themselves from democratic political processes. A medical explanation proposes that some Pythagoreans may have suffered from favism, a genetic condition common in Mediterranean populations that makes consumption of fava beans potentially fatal. If Pythagoras or early members had this condition, the prohibition might have begun as practical health advice that later acquired mystical significance. Modern scholars, like Marcel Détienne, have argued that the bean prohibition should be understood symbolically rather than literally. Beans represented the chaotic, impure, decaying aspects of material existence that philosophers must transcend. Whether members actually avoided beans or the taboo was metaphorical remains debated. Afternoon activities included teaching, where more advanced members instructed initiates, and periods of silent reflection. Evenings featured group discussions of philosophical problems, ethical dilemmas, and progress in mathematical studies. Before sleep, each member was supposed to review the day, examining their actions, identifying mistakes, and planning improvements. This nightly self-examination, a practice that influenced Stoic philosophy and later Christian monastic traditions, aimed at continuous moral refinement. The Pythagoreans maintain numerous other rules that strike modern readers as bizarre. They prohibited stirring fire with iron tools, using only wood. They insisted on smoothing out body impressions left in bedding after rising. They avoided looking in mirrors by lamplight. They refused to turn around when leaving home, walking forward without looking back. Some of these rules may have had practical origins that became ritualized. Not stirring fire with metal prevents sparks and damage to tools. Smoothing bedding prevents vermin from nesting. Not looking in mirrors by lamplight avoids the distortion and shadows that might be disturbing. But Pythagoreans themselves interpreted these rules symbolically, as reminders of deeper truths. Smoothing bedding symbolized not becoming attached to temporary resting places. Not looking back when leaving represented commitment to philosophical progress without nostalgia for previous, less enlightened states. The community had distinct grades of membership with different privileges and responsibilities. New entrants were called listeners and underwent years of silence, literally forbidden from speaking while they absorbed teachings. After proving their commitment and progress, they could advance to full membership as mathematicians, actively participating in discussions and research. The highest members, called politicians, handled community governance and external relations. This hierarchical structure was explicitly anti-egalitarian. The Pythagoreans believed not everyone was equally capable of philosophical understanding, and society should reflect these natural differences. Those who had purified their souls through study and discipline deserved authority over those still trapped in ignorance and bodily desires. This elitism would have profound political consequences we will explore in the next section. Women participated in Pythagorean communities, unusual for ancient Greece. Sources mention several prominent female Pythagoreans, most famously Theano, described as either Pythagoras' wife or student, or both. Fragments attributed to her discuss mathematics, ethics, and the nature of virtue. Whether these fragments are authentic or later inventions remains debated, but they show that later tradition remembered the Pythagorean community as including women in philosophical activities. However, we should not romanticize Pythagorean gender equality. Women in the community still faced restrictions and were often valued primarily for supporting male philosophers rather than as independent thinkers. The inclusion of women was progressive by ancient standards, but far from contemporary equality. The Pythagorean way of life aimed at complete transformation of the person. Every aspect of daily existence, from what you ate to how you walked to what you thought about before sleep, was structured to purify the soul and align it with cosmic order. This totalizing approach distinguished Pythagoreanism from more purely intellectual philosophical schools. You could study with the sophists or later with Aristotle without changing how you lived, but you could not be a Pythagorean without embracing the entire lifestyle. This raises important questions about the relationship between philosophy and life that remain relevant today. Should philosophy remain purely theoretical, an intellectual exercise separate from practical living? Or should philosophical convictions necessarily transform how we live, making philosophy a guide to existence? The Pythagoreans insisted on the latter, arguing that philosophy without life transformation is empty speculation. Modern philosophy has largely abandoned the Pythagorean model. Philosophy departments teach logical analysis and theoretical problems without expecting students to adopt particular lifestyles. We have separated intellectual from ethical training, treating philosophical knowledge as academically interesting but practically neutral. Yet this separation troubles some contemporary philosophers. Pierre Hadot argued that ancient philosophy, including Pythagoreanism, should be understood as spiritual exercises aimed at transformation rather than just theoretical doctrines. Michel Foucault explored how ancient philosophical practices involved technologies of the self, methods for cultivating particular kinds of subjectivity. Both suggest we have lost something important by reducing philosophy to academic theorizing divorced from lived practice. The Pythagorean lifestyle also faced practical problems that contributed to the movement's decline. Communal living works well for small dedicated groups, but becomes difficult at scale. As Pythagorean communities grew, maintaining ideological purity and practical discipline became harder. Disputes arose about interpreting rules, relaxing requirements, and accommodating individual differences. The dietary restrictions and ascetic practices could also damage health if taken to extremes. Ancient sources mention Pythagoreans who became weak or ill from excessive fasting or restricted diets. The line between healthy simplicity and unhealthy deprivation is often unclear, and different individuals have different nutritional needs that rigid rules cannot accommodate. Furthermore, the demand for complete lifestyle commitment limited who could join. Only those with sufficient wealth and leisure to abandon normal work and family obligations could become full Pythagoreans. This made the movement necessarily elite and small-scale, unable to expand broadly through society. The extensive rules and rituals could also descend into empty formalism, following prescriptions mechanically without understanding their purpose. This is a danger in any rule-based ethical system that means become mistaken for ends. You can smooth your bedding and avoid beans while remaining morally and intellectually unchanged, performing rituals without genuine transformation. Later, Pythagoreans recognized these problems and split between those emphasizing external practices versus internal understanding. The acosmatics focused on maintaining traditional rules exactly as received from the master. The mathematicians emphasized intellectual insight, arguing that understanding mathematical and philosophical truths mattered more than dietary rules and daily rituals. This division reflects a tension inherent in any system that combines practical living with theoretical knowledge. Despite these problems, the Pythagorean attempt to integrate philosophy with life remains valuable. They recognized that intellectual convictions should manifest in concrete actions, that proclaiming values while living contrary to them reveals either hypocrisy or failure to truly understand those values. Contemporary movements trying to live philosophically, from voluntary simplicity to effective altruism to various spiritual communities, echo Pythagorean themes. They share the conviction that how we live matters morally and intellectually, that certain lifestyles promote human flourishing while others diminish it, and that communities can support individuals in living according to their values. The Pythagorean model also reminds us that philosophy historically offered more than academic credentials or intellectual puzzles. It promised meaning, purpose, community, and practical guidance for living well. Whether modern philosophy should return to this model or has rightly moved beyond it remains contested, but the Pythagorean way of life shows us an alternative to purely theoretical philosophy that many find compelling. Part 8. Political Philosophy and its Consequences. The political dimension of Pythagoreanism reveals the dark side of their philosophy, how beliefs about the soul, knowledge and cosmic order translated into concrete political arrangements that provoked violent resistance and ultimately destroyed the movement as a cohesive organization. Pythagorean political philosophy began from a seemingly innocent premise that those who understand truth should guide those who do not. Since the Pythagoreans believed they possessed knowledge of cosmic order through mathematical and philosophical study, they concluded they were naturally fitted to govern. This was not mere ambition, but followed logically from their metaphysics. If the universe is ordered mathematically, and some people understand this order while others do not, then those who understand should structure society to reflect cosmic harmony. In Croton and other southern Italian cities, Pythagorean communities gained substantial political influence during the late 6th and early 5th centuries BCE. They formed what we might call a political party or faction, working to install sympathetic rulers and enact policies aligned with their philosophical principles. Sources suggest they generally supported aristocratic governments against democratic movements, though the evidence is fragmentary and sometimes contradictory. The Pythagorean political ideal was rule by the wise, what Greeks called aristocracy in its original sense, rule by the best. But who counts as best, and how do we identify them? For Pythagoreans, the best were those who had purified their souls through philosophical discipline, who understood mathematical harmony, who lived according to reason rather than appetite. Not coincidentally, this meant Pythagoreans themselves. This political philosophy assumes that virtue and knowledge can be clearly identified, and that those possessing them will rule justly. But this assumption is enormously problematic. How do we verify that someone truly possesses philosophical wisdom rather than merely claiming it? Who judges the judges, and what prevents the supposedly wise from using their authority for selfish purposes? The Pythagoreans apparently believed their lifestyle and community structure solved these problems. Communal property eliminated personal economic motives for corruption. Years of silent listening before speaking ensured leaders were genuinely committed rather than ambitious seekers of power. Mathematical and philosophical training developed objectivity and impartiality. But these safeguards proved insufficient. Human nature resists such complete transformation, and absolute conviction of one's own righteousness often enables rather than prevents abuse of power. Historical evidence suggests Pythagorean political rule was often repressive, enforcing their moral and dietary codes on unwilling populations and suppressing dissent as ignorance that needed correction. Around 500 BCE, violent anti-Pythagorean uprisings erupted across southern Italy. Democratic factions, perhaps with popular support, attacked Pythagorean meeting houses, killing many members and driving others into exile. Ancient sources describe these attacks as sudden and brutal, with Pythagoreans burned alive in their assembly halls. What provoked such extreme violence? The sources are biased, either sympathetic to Pythagoreans and portraying them as innocent martyrs, or hostile and describing them as tyrannical oppressors. The truth likely lies between these extremes. The Pythagoreans probably did exercise political power in ways that antagonized significant portions of the population, while the violent response likely exceeded what their actual offences warranted. Several factors probably contributed to the backlash. First, Pythagorean secrecy and exclusivity bred suspicion. When an elite group claims special wisdom that justifies political authority but refuses to share that wisdom with outsiders, resentment builds. People naturally distrust those who claim to know better while refusing to explain their reasoning. Second, Pythagorean lifestyle requirements may have been imposed on non-members. If you tried to enforce vegetarianism and bean prohibition throughout a city, you would face resistance from butchers, farmers, and anyone who enjoyed meat. Religious dietary rules are tolerable when voluntary, but become tyrannical when legally mandated. Third, Pythagorean political philosophy was explicitly anti-democratic. They believed the many should submit to the few who understood truth. In an era when democratic ideals were gaining strength in Greek cities, this aristocratic elitism naturally provoked democratic opposition. The conflict between Pythagorean rule by the wise and democratic rule by the people represented fundamentally incompatible political visions. The violence of the anti-Pythagorean uprisings decimated the movement. Many members were killed, survivors scattered, and the institutional structure of Pythagorean communities was destroyed. Pythagoreanism continued as an intellectual tradition and loose network of sympathizers, but never again as organized political communities exercising local power. This catastrophic failure raises profound questions about how philosophy should relate to politics. The Pythagoreans believed philosophical truth should directly guide political arrangements. That understanding cosmic order qualifies one to organize human society. But this belief led to disaster when implemented, producing repression, resentment, and violent backlash. Does this mean philosophy should avoid politics entirely? That philosophical knowledge provides no guidance for political questions? Or does it mean the Pythagoreans simply got the relationship wrong, that philosophical insight should inform politics without claiming to perfectly determine political arrangements? Plato, heavily influenced by Pythagoreanism, grappled with these questions in the Republic and later dialogues. He proposed that philosopher kings, those who understood eternal truths about the good, should rule absolutely. But even Plato acknowledged that such perfect rule was unlikely in practice, and in his later work Laws he developed more realistic political proposals with checks on philosophical authority. Aristotle explicitly rejected Pythagorean and Platonic political philosophy. He argued that politics requires practical wisdom about contingent human affairs, not theoretical knowledge of eternal truths. Mathematical expertise does not translate to political expertise because politics deals with variable circumstances, competing interests, and value conflicts that mathematical reasoning cannot resolve. Good government requires experience, judgment, and responsiveness to particular situations, not just philosophical understanding. The Pythagorean political failure has echoed through history whenever intellectuals claim that theoretical knowledge qualifies them for unchecked power. Marxist-Leninist vanguard parties claimed to understand historical laws that justified their dictatorship. Technocrats claim expertise in economics or policy analysis justifies sidelining democratic deliberation. Each time, the pattern resembles Pythagorean rule by the wise, with similar problems. The core problem is that political authority cannot be justified purely through claims about knowledge or virtue. Even if some people genuinely know more or are more virtuous than others, concentrating power in their hands creates dangers that outweigh benefits. Power corrupts even the wise and virtuous. Knowledge in one domain does not guarantee competence in others. And people have legitimate interests in governing themselves, even if they lack philosophical training. Modern liberal democracy, with its separation of powers, periodic elections, and constitutional constraints, represents a rejection of Pythagorean political philosophy. It assumes no one, however wise, should wield unchecked authority. Instead, power should be distributed, limited, and accountable to those it governs. This may produce less elegant or efficient government than enlightened philosopher rule, but it prevents the disasters that result when philosophers become tyrants. Yet the Pythagorean intuition that knowledge should inform politics remains valuable. We do want expert input on technical questions like public health, infrastructure, or environmental policy. The question is how to incorporate expertise without establishing expert rule, how to benefit from specialized knowledge while maintaining democratic accountability. Contemporary debates about the role of scientists and technocrats in policymaking essentially replay Pythagorean political questions. Should climate scientists determine environmental policy? Or should they advise elected officials who make final decisions? Should central bankers have independence from democratic oversight? Or should monetary policy be democratically controlled? Should philosophers and ethicists guide biomedical research? Or should they merely offer input while researchers and the public decide? These questions have no easy answers. But the Pythagorean experience suggests caution about claims that expertise justifies authority. Knowledge is valuable and should be consulted, but it does not entitle the knowledgeable to rule the less knowledgeable. The violent destruction of Pythagorean political power also reminds us that political stability requires legitimacy, and legitimacy requires some form of consent from the governed. You can have the most philosophical justified government imaginable, but if the population rejects its authority, it will fail. Political philosophy must grapple with actual human psychology and social dynamics, not just abstract principles of justice. Interestingly, aspects of Pythagorean political thought survived their political disaster and influenced later traditions. The emphasis on education as preparation for citizenship, the idea that political leaders need special training and virtue, the concern that pure democracy can degenerate into mob rule. All these Pythagorean themes reappear in subsequent political philosophy. The American founding fathers, many influenced by classical philosophy, incorporated some Pythagorean concerns into constitutional design. They created a republic rather than a pure democracy, with representatives chosen for virtue and wisdom rather than direct popular rule. They established educational requirements for office and systems of checks and balances to prevent both tyranny of elites and tyranny of majorities. While they did not go nearly as far as Pythagorean rule by philosophers, They shared the concern that successful politics requires cultivated judgment and restraint of immediate popular passions. The lasting legacy of Pythagorean political philosophy is thus ambivalent. Their attempt to establish philosopher rule failed catastrophically, teaching important lessons about the limits of expertise and the dangers of unchecked intellectual authority. But their concern that politics requires wisdom, virtue, and understanding of cosmic order broadly understood continues to resonate. The challenge is finding political arrangements that benefit from philosophical insight without granting philosophers political supremacy, that combine expert knowledge with democratic accountability, that pursue justice and truth while respecting human freedom and dignity. Part 9. Influence and Legacy. The influence of Pythagoreanism on Western thought cannot be overstated. For over 2,500 years, Pythagorean ideas have shaped mathematics, science, philosophy, religion, art, and music. Even when later thinkers rejected specific Pythagorean doctrines, they often did so within conceptual frameworks that Pythagoreanism helped establish. The most immediate and profound influence was on Plato, arguably the most influential philosopher in Western history. Plato encountered Pythagorean ideas through his teacher Socrates, who had some contact with Pythagorean thinkers, and later through direct engagement with Pythagorean philosophers in southern Italy. Many of Plato's central doctrines show clear Pythagorean origins, though he developed them in distinctive ways. Plato's theory of forms, his most famous philosophical contribution, is essentially an elaboration of Pythagorean metaphysics. The Pythagoreans believed numbers were eternal realities that physical objects imperfectly instantiated. Plato generalized this, proposing that all abstract concepts, not just numbers, correspond to eternal forms that particular things imperfectly resemble. Just as many different triangles all participate in the form of triangle, many different just actions all participate in the form of justice. This theory allowed Plato to address fundamental philosophical questions about how universals relate to particulars, how knowledge is possible despite constant change, and why some things are better than others. But the conceptual foundation came from Pythagorean number theory, and the insight that abstract entities are more real than concrete particulars. Plato's epistemology also derives from Pythagorean sources. The theory of recollection, that learning is remembering what the soul knew before birth, appears explicitly in Plato's Meno and Phaedo. Plato uses Pythagorean-style mathematical examples to illustrate how we can grasp eternal truths through reason independently of sensory experience. The divided line in the Republic, distinguishing levels of reality and corresponding types of knowledge, places mathematics at a crucial intermediate stage between sensory perception and pure philosophical insight, reflecting Pythagorean views about mathematics as the path to higher knowledge. Plato's Ethics also shows Pythagorean influence. The idea that the soul needs purification from bodily contamination, that philosophy is preparation for death by practicing separation of soul from body, that virtue is a kind of harmony, all these Platonic themes echo Pythagorean teaching. The tripartite division of the soul in the Republic into rational, spirited, and appetitive parts reflects Pythagorean ideas about internal harmony, analogous to musical consonance. Even Plato's political philosophy, despite advocating philosopher-king rule that the Pythagoreans had disastrously attempted, develops Pythagorean themes about the need for wisdom in governance and the dangers of ignorant democratic rule. Through Plato, Pythagorean ideas entered the bloodstream of Western philosophy and remained there. Every philosopher who engaged with Plato, which means essentially every significant Western philosopher, thereby encountered Pythagorean concepts. Aristotle, Plato's student, rejected many Pythagorean and Platonic doctrines, but still absorbed their influence. His criticism of the Pythagorean theory that numbers are the substance of things shaped how later philosophers thought about the relationship between mathematics and reality. His emphasis on mathematical sciences in his classification of knowledge reflects Pythagorean elevation of mathematical understanding. Even his critiques kept Pythagorean ideas alive by taking them seriously enough to argue against. The Hellenistic schools of philosophy that emerged after Aristotle, particularly the Stoics and Neoplatonists, revived Pythagorean themes. Stoic cosmology, with its emphasis on cosmic harmony and rational order governing nature, shows Pythagorean influence. Their ethical practices of self-examination and purification echo Pythagorean spiritual exercises. Neoplatonism, especially as developed by Plotinus in the 3rd century CE, explicitly synthesized Platonic and Pythagorean elements. Plotinus's emanation theory, where reality flows from a transcendent one through descending levels of being, combines Platonic forms with Pythagorean numerology and harmony. Neoplatonists practice mathematics as spiritual discipline, seeing geometric and arithmetic study as methods for elevating the soul toward unity with the divine. When Christianity became the dominant philosophical and religious framework in late antiquity, it absorbed Pythagorean ideas through Platonic and Neoplatonic channels. Augustine, the most influential early Christian philosopher, was heavily influenced by Neoplatonism, and therefore indirectly by Pythagoreanism. His belief that eternal truths exist in the mind of God, that the material world is less real than spiritual reality, that mathematical knowledge reveals divine order, all show Pythagorean influence mediated through Plato and Plotinus. Medieval Christian philosophy continued this Pythagorean inheritance. Boethius, whose works formed the foundation of medieval education, wrote extensively on music theory using Pythagorean principles. His distinction between musica mundana, cosmic harmony, and musica humana, human harmony, directly transmits Pythagorean concepts to medieval thought. Medieval number symbolism, finding sacred meanings in biblical numbers, represents Pythagorean numerology baptized into Christianity. Theologians interpreted the Trinity mathematically, seeing 3 as the first number transcending duality and thus appropriate for God's nature. Architectural proportions of Gothic cathedrals followed mathematical ratios believed to reflect divine harmony, applying Pythagorean principles to sacred buildings. The Renaissance witnessed a dramatic revival of explicit Pythagoreanism. Marsilio Ficino translated Plato and Neoplatonic texts into Latin, making them widely available to European intellectuals who embraced Pythagorean themes enthusiastically. Renaissance. Neoplatonism combined Christian theology with classical philosophy, producing elaborate systems of correspondence between mathematics, music, astrology, and theology. Artists and architects applied mathematical proportions systematically, believing beauty derived from numerical harmony. Leon Battista Alberti based architectural theory on musical ratios, designing buildings according to the same proportions that create consonant musical intervals. Painters like Piero della Francesca used geometric construction and perspective systems to create images believed to embody mathematical perfection. The scientific revolution of the 16th and 17th centuries was deeply Pythagorean in spirit, even when rejecting specific Pythagorean claims. Copernicus justified heliocentrism partly through appeal to mathematical elegance and the superiority of simple geometric arrangements, pure Pythagorean reasoning. Kepler, as we have discussed, explicitly pursued Pythagorean harmony in the heavens and made genuine astronomical discoveries in the process. Galileo's famous declaration that the book of nature is written in the language of mathematics, that without mathematics we wander in a dark labyrinth, is perhaps the most concise statement of Pythagorean scientific philosophy ever articulated. Galileo believed mathematical relationships revealed the fundamental structure of physical reality, that geometric and arithmetic truths governed natural phenomena. This conviction drove his experimental method and mathematical analysis of motion, creating modern physics. Newton synthesized this Pythagorean approach into a comprehensive mathematical physics. His Principia Mathematica demonstrated that diverse phenomena, from falling apples to planetary orbits to tides, all follow universal mathematical laws. The Pythagorean dream of cosmic mathematical harmony found its greatest vindication in Newtonian mechanics, though Newton's mathematics was far more sophisticated than anything the ancient Pythagoreans could have imagined. The Pythagorean influence on music theory proved especially durable. Until the 19th century, Western music theory remained fundamentally Pythagorean, based on the discovery that simple numerical ratios produce consonant intervals. The temperament systems used to tune instruments were variations on Pythagorean tuning, compromises between mathematical purity and practical performance needs. Composers consciously employed numerical structure in their works. Johann Sebastian Bach's compositions are famous for intricate mathematical patterns, canons and fugues built on precise numerical relationships between voices. Whether Bach saw these structures as merely technical devices or as embodying cosmic harmony remains debated, but the Pythagorean tradition of connecting music and mathematics clearly influenced his compositional approach. The Enlightenment maintained Pythagorean commitments while secularizing them. Leibniz believed that reality is fundamentally mathematical, that God calculates when creating the world, and that understanding these calculations reveals divine wisdom. His development of calculus was driven partly by Pythagorean-inspired desire to find the mathematics of change and motion. Kant's philosophy shows complex Pythagorean influence. His claim that mathematics provides synthetic a priori knowledge, truths that are both necessary and informative about experience, attempts to explain why mathematics applies to nature so successfully. Kant argued that space and time are forms our minds impose on experience, and mathematics describes these forms, which explains mathematical science's success without requiring that numbers are the substance of reality. This sophisticated answer to Pythagorean questions shaped philosophy for the next 2 centuries. The 19th century saw Pythagoreanism fragment into different currents. Mathematical physics continued its triumphant march, with Maxwell's equations describing electromagnetism and statistical mechanics explaining thermodynamics, all confirming that mathematical law governs natural phenomena. But mathematics itself became increasingly abstract, no longer obviously connected to physical reality or mystical harmony. The discovery of non-Euclidean geometries in the early 1800s shattered the assumption that mathematical truth is unique and absolute. If multiple contradictory geometric systems are all mathematically consistent, which one describes real space? This question challenged Pythagorean confidence that mathematics reveals the structure of reality. Simultaneously, Pythagorean themes persisted in Romantic philosophy and occult traditions. Schopenhauer's philosophy emphasized music as the direct manifestation of the will, the fundamental reality underlying appearances, echoing Pythagorean beliefs about music's metaphysical significance. Occult movements, like Theosophy, revived Pythagorean numerology and mysticism, though often in garbled, historically inaccurate forms. Nietzsche's discussion of the Apollonian and Dionysian in The Birth of Tragedy engaged with Pythagorean themes about harmony, order, and the tension between rational structure and chaotic creativity. While Nietzsche criticized Socratic and Platonic rationalism as life-denying, he acknowledged the psychological power of Pythagorean Platonic visions of cosmic order. The 20th century brought both vindication and complication of Pythagorean ideas. Einstein's general relativity showed that the geometry of space-time is not fixed, but dynamic, determined by matter and energy distribution. The universe has a mathematical structure far stranger than the Pythagoreans imagined, curved four-dimensional space-time rather than three-dimensional Euclidean space. Yet this confirmed the Pythagorean insight that reality is fundamentally mathematical, just with mathematics far more abstract than simple ratios. Quantum mechanics pushed mathematical abstraction further. Subatomic reality is described through complex-valued wave functions in infinite-dimensional Hilbert spaces, mathematical structures with no direct physical interpretation. The theory works spectacularly well for predictions, but what it means about reality remains deeply puzzling. Are these mathematical structures real or merely calculational tools? The question is Pythagorean, and physicists disagree about the answer. The philosopher Bertrand Russell, who made fundamental contributions to mathematical logic, argued that mathematics is the only subject where we really know what we are talking about. This echoes Pythagorean confidence in mathematical knowledge's superiority to empirical observation. Russell's logicism, the program to reduce mathematics to pure logic, attempted to explain mathematical certainty but ultimately failed when Gödel proved inherent limitations in formal systems. Gödel's incompleteness theorems, published in 1931, showed that any consistent mathematical system complex enough to include arithmetic contains true statements that cannot be proven within that system. This seemed to undermine Pythagorean confidence that mathematical truth is completely accessible to reason. But Gödel himself interpreted his results differently, arguing they show mathematical intuition exceeds formal proof, that we can grasp mathematical truths that no mechanical procedure can verify. This position is surprisingly Pythagorean, suggesting mathematical knowledge comes from a kind of direct insight beyond algorithmic reasoning. Contemporary physics continues wrestling with Pythagorean questions. String theory proposes that fundamental particles are vibrating strings in 10 or 11 dimensions, reviving Pythagorean themes of vibration and hidden dimensions in startlingly literal form. Whether string theory is correct remains unknown. It makes few testable predictions, and some physicists dismiss it as mathematical philosophy rather than empirical science. But its popularity shows the continuing appeal of Pythagorean-style explanations that ground physical reality in mathematical structures. The mathematical physicist Max Tegmark has argued for the mathematical universe hypothesis, explicitly reviving Pythagorean metaphysics. Tegmark proposes that physical reality is not merely described by mathematics, but is mathematics, that the universe is literally a mathematical structure. He argues this explains why mathematics is so unreasonably effective in physics. It is not that we use mathematics to describe a non-mathematical reality, but that we are mathematical structures studying ourselves. Critics respond that this is incoherent mysticism, confusing descriptions with things described. How can mathematics, which is abstract and causally inert, be identical to the concrete, causally efficacious physical world? The debate exactly parallels Aristotle's critique of Pythagorean number metaphysics 2,400 years ago, showing these fundamental questions remain unresolved. In computer science and information theory, Pythagorean ideas appear in new guises. The suggestion that the universe is fundamentally information, that physical laws are computational processes, that reality is ultimately bits rather than atoms, represents digital age Pythagoreanism. If everything reduces to information processing describable mathematically, then numbers, or at least discrete computational states, are indeed the substance of reality. Artificial intelligence and machine learning have revived questions about whether mathematical patterns in data reveal genuine understanding or merely statistical correlation. Neural networks find mathematical regularities in images, text, and other data without explicit programming. Do these mathematical patterns constitute knowledge? Or are they sophisticated pattern matching without comprehension? The question echoes Pythagorean debates about whether grasping mathematical relationships constitutes genuine understanding of reality. In contemporary culture, Pythagorean ideas persist in both sophisticated and debased forms. Serious scientists and philosophers continue debating whether mathematics is discovered or invented, whether the universe is fundamentally mathematical, whether beauty and elegance are guides to truth. Meanwhile, popular pseudoscience invokes Pythagorean-sounding ideas about cosmic vibrations, frequency healing, and numerological mysticism, usually without understanding genuine Pythagorean philosophy. The lasting legacy of Pythagoreanism is thus paradoxical. On one hand, the core insight that mathematical relationships reveal deep truths about reality has been spectacularly vindicated by modern science. On the other hand, specific Pythagorean doctrines about number mysticism, cosmic music, and reincarnation have been abandoned by serious thinkers. We are all Pythagoreans in method, seeking mathematical laws of nature, but few of us are Pythagoreans in metaphysics, believing numbers are the substance of things. Yet perhaps this separation is less complete than it appears. When physicists claim that reality is fundamentally quantum fields described by equations, are they really so different from Pythagoreans claiming reality is fundamentally numbers? When neuroscientists describe consciousness as patterns of neural firing rates, Are they not reducing mental life to numerical relationships? The boundary between using mathematics to describe reality and claiming reality is mathematical may be less clear than we assume. The Pythagorean legacy also lives in educational practices. Mathematics remains central to the curriculum, considered essential for developing rational thought. We still believe, as the Pythagoreans did, that studying mathematics trains the mind in abstract reasoning valuable beyond mathematical applications. Whether we should also revive Pythagorean integration of mathematics with ethics, aesthetics, and spiritual development remains contested. Part 10. Critiques, Failures, and Modern Debates. Having explored Pythagorean philosophy and its influence, we must now critically examine where Pythagoreanism failed, what valid objections have been raised against it, and what contemporary scholars debate about its legacy. The most fundamental critique, articulated by Aristotle and still relevant today, challenges the coherence of claiming that numbers are substances. Aristotle argued this confuses a description with what is described, treating an attribute or property as if it were the thing itself. Numbers describe quantities and relationships, but to say an object is a number seems to make a category mistake, like saying the colour red is a wavelength rather than that red light has a particular wavelength. Modern philosophy distinguishes between ontology, what exists, and epistemology, how we know. The Pythagorean error, critics argue, is conflating these, assuming that because mathematical knowledge is certain and eternal, mathematical objects must be more real than physical objects. But this does not follow. Mathematical truths may be necessary without numbers themselves existing as entities. Contemporary nominalists argue that numbers are simply concepts or linguistic conventions, not existing entities at all. When we say there are 3 apples, we are not claiming the number 3 exists independently, but using a conceptual tool to describe the apples. On this view, Pythagorean metaphysics is fundamentally confused, reifying abstractions. However, nominalism faces its own difficulties explaining why mathematics works so well in science. If numbers are arbitrary human inventions, why do they describe natural phenomena so precisely? Why can we predict eclipses, design computers, and cure diseases using mathematical models if mathematics has no objective connection to reality? This leads to what philosophers call the indispensability argument for mathematical Platonism. If science cannot do without mathematics, and science aims to describe reality accurately, then mathematical entities must be real in some sense. This argument partially vindicates Pythagorean metaphysics while avoiding their specific claims about particular numbers having mystical significance. The discovery of irrational numbers exposed a critical failure in Pythagorean philosophy. If everything is number, and number means ratios of whole numbers, then incommensurable magnitudes should not exist. But they do exist, revealed by rigorous proof that the Pythagoreans themselves developed. This showed that their fundamental metaphysical commitment was wrong. Reality contains aspects that exceed rational numerical description. The Pythagorean response, essentially abandoning universal commensurability while maintaining that mathematics is fundamental, represents intellectual flexibility, but also shows their system was not as coherent as claimed. When your central doctrine contradicts proven mathematical truth, something must change. Later, mathematical discoveries revealed further limitations. Complex numbers, which involve the square root of -1, cannot be interpreted as magnitudes in any obvious way. Transfinite numbers, describing different sizes of infinity, exceed anything the Pythagoreans could have imagined. Non-Euclidean geometries showed that mathematical truth is not unique and absolute. Each advance in mathematics moved further from Pythagorean assumptions about simple numerical relationships governing reality. The harmony of the spheres proved empirically false. Planets do not produce sounds, their orbital ratios do not match musical intervals, and the theory made no successful predictions. It was beautiful poetry, but bad science, exemplifying how aesthetic preferences can mislead if not disciplined by observation. Kepler's attempt to find musical harmonies in planetary orbits failed despite his astronomical genius. This failure is instructive, showing that even brilliant scientists can waste years pursuing elegant but wrong ideas. The lesson is not to abandon aesthetic criteria entirely, but to remain skeptical and demand empirical confirmation. Pythagorean numerology, finding mystical significance in particular numbers, has no legitimate basis. That 10 is sacred or 7 is virginal reflects human psychology and cultural associations, not objective cosmic facts. The same criticism applies to contemporary pseudoscience claiming magical properties for certain frequencies or numerical patterns. Without testable predictions and experimental confirmation, numerological claims are meaningless. The reincarnation doctrine faces severe empirical and philosophical problems. We have no reliable evidence for past life memories that cannot be explained by fraud, imagination, or cultural transmission of information. The mechanism by which an immaterial soul could inhabit successive bodies remains unexplained. What persists across incarnations, if memory and personality do not, and if nothing persists, in what sense is it the same soul? More fundamentally, neuroscience has shown that consciousness and personality depend on brain structure and chemistry. Damage specific brain regions, and you lose specific capacities, from language to moral judgment to self-recognition. This strongly suggests consciousness is a product of physical brain processes, not an independent soul that could survive bodily death and reincarnate. Some philosophers argue that reincarnation is logically incoherent. Personal identity requires psychological continuity through memory and character. If you cannot remember previous lives and have a completely different personality, the being in the previous life was not you in any meaningful sense. Calling it your soul is mere labeling without explanatory content. The Pythagorean political philosophy failed catastrophically in practice and remains theoretically problematic. Rule by self-proclaimed wise people tends toward oligarchy and tyranny, not enlightened governance. The assumption that philosophical knowledge qualifies one for political authority ignores that politics requires different skills than theoretical understanding, including empathy, judgment about practical affairs, and ability to build consensus among people with diverse interests and values. Modern democratic theory rejects Pythagorean elitism, while acknowledging expertise has value. The solution is not rule by the wise, but institutional arrangements that incorporate expert knowledge while maintaining democratic accountability. Representative democracy with advised policymaking splits the difference between pure technocracy and pure populism. The Pythagorean way of life, while admirable in its holistic integration of philosophy and practice, proved difficult to sustain and exclusionary by nature. Communal living works temporarily for small groups, but faces scaling problems and internal disputes. Dietary restrictions and ascetic practices can damage health if taken to extremes. The demand for complete lifestyle commitment limited membership to those with sufficient resources and leisure, making Pythagoreanism accessible only to elites. Contemporary scholars debate how to interpret Pythagorean secrecy and the oral tradition. Some argue secrecy was pedagogical. Information must be revealed gradually for proper understanding. Others suggest it was simply elitism, maintaining insider-outsider boundaries that reinforced group identity and social status. The lack of written texts makes it impossible to know what Pythagoras himself actually taught, creating interpretive freedom that has allowed wildly different reconstructions. The historian Walter Burkert argued that we should distinguish sharply between early Pythagorean religious practices and later mathematical work attributed to Pythagoreans. He suggested that Pythagoras himself was primarily a religious leader and miracle worker, with mathematical and scientific associations being later accretions. This radical skepticism challenges traditional narratives but fits the fragmentary evidence. Other scholars like Karl Huffman argue for more historical continuity between religious and mathematical Pythagoreanism. They point to the internally consistent worldview that mathematics provided a religious path to truth, and suggest completely separating these aspects is artificial. This scholarly debate matters because it shapes how we understand the relationship between science and religion, reason and mysticism. If Pythagoreanism successfully integrated these domains, it models a holistic approach to knowledge that modernity has lost. If the integration was always tenuous and the religious and mathematical aspects really separate, then modern separation of science from religion represents natural development rather than decline. Contemporary debates about mathematical Platonism continue Pythagorean controversies. Philosophers like Hartree Field argue that mathematics is a useful fiction that need not correspond to any reality, defending nominalism. Others, like Penelope Maddy, argue that mathematics is about abstract structures that exist independently of physical reality or human minds, a neo-Pythagorean position. These debates remain unresolved, suggesting Pythagoras raised questions philosophy has not yet answered satisfactorily. In philosophy of science, the debate about the role of aesthetic criteria like elegance and simplicity in theory, choice, echoes Pythagorean controversies. Thomas Kuhn argued that scientists do use such criteria, but that these reflect subjective values, not objective truth. Others maintain that elegance and simplicity are evidence for truth because nature really is elegant and simple, a Pythagorean assumption. The disagreement cuts to fundamental questions about scientific methodology and the nature of reality. The effectiveness of mathematics in science, what Eugene Wigner called unreasonable effectiveness, remains philosophically puzzling. Why should abstract structures invented or discovered by human minds describe physical reality so accurately? The Pythagorean answer, that reality is fundamentally mathematical, provides one explanation but raises its own difficulties. Alternative explanations, like that brains evolved to perceive mathematical patterns because such perception was evolutionarily advantageous, remain speculative. Cognitive science offers new perspectives on why humans find mathematical harmony aesthetically pleasing. Perhaps our brains are wired to prefer certain patterns and ratios, making musical consonants and visual proportions based on simple ratios feel beautiful, not because they reflect cosmic order, but because natural selection favored pattern recognition abilities. This evolutionary explanation challenges Pythagorean claims about objective beauty while explaining the psychological power of their ideas. The quantum physics revolution raised new questions about mathematical reality. Wave functions in quantum mechanics are not directly observable. Only their squared amplitudes correspond to probabilities of measurement outcomes. This seems to make mathematical structures more fundamental than physical properties, vindicating Pythagoreanism in strange ways. But interpretations of quantum mechanics remain contested, with some treating wave functions as real physical entities, others as merely calculational tools, and still others proposing entirely different ontologies. Contemporary physics faces a reproducibility of Pythagorean temptations. String theory is mathematically beautiful but makes few testable predictions, leading critics to accuse it of being aesthetics, masquerading as science. Multiverse theories propose unobservable universes to explain why our universe appears fine-tuned for life, raising questions about whether this is legitimate physics or metaphysical speculation. In both cases, the debate is whether mathematical elegance justifies belief absent empirical confirmation, a pure Pythagorean question. Lessons from Pythagorean failures remain relevant. First, metaphysical commitments should be held tentatively, subject to revision based on evidence and argument. The Pythagoreans turned their insights into dogmas, sacrificing truth to maintain systematic coherence. Second, aesthetic preferences are useful guides, but unreliable guarantees of truth. Simple, beautiful theories are often true, but not always, and empirical testing remains essential. Third, political authority cannot be justified purely through claims about knowledge or virtue, regardless of how compelling those claims seem. Finally, integrating different aspects of life, intellectual, ethical, aesthetic, spiritual, into coherent wholes is valuable but difficult. The Pythagoreans achieved this integration, but at the cost of rigidity, exclusion, and eventual collapse. Modern fragmentation of knowledge into specialized disciplines has costs, but also benefits in allowing expert development and avoiding totalizing systems that claim complete truth. The ultimate assessment of Pythagoreanism must be mixed. They made genuine discoveries in mathematics and music theory that remain valid. They pioneered the application of mathematics to nature that eventually produced modern science. They raised profound philosophical questions about the nature of reality, knowledge and value that remain unresolved. But they also promoted mystical numerology with no empirical basis, political elitism that led to violence, and metaphysical dogmas that hindered as well as helped scientific progress. They created a religious cult that imposed its beliefs on others and responded to internal contradictions with suppression rather than revision. Pythagoreanism is thus neither pure wisdom to be recovered nor simple error to be dismissed. It represents an ambitious attempt to understand reality that succeeded brilliantly in some respects and failed dramatically in others. We honor their genuine insights while learning from their mistakes, using mathematics to investigate nature without claiming it is nature, valuing philosophical reflection without granting philosophers political supremacy, and integrating different aspects of life while maintaining intellectual humility about what we actually know. The Pythagorean legacy endures not because they got everything right, but because they asked the right questions and pursued answers with passionate commitment. That combination of intellectual ambition and practical dedication to living according to one's beliefs remains worthy of respect, even when specific beliefs prove wrong. Every serious attempt to understand reality and live meaningfully builds on Pythagorean foundations, whether consciously or not, making us all inheritors of a tradition that began 2,500 years ago on the coast of southern Italy with a charismatic teacher who saw numbers in everything and convinced his followers that the universe sings. We have journeyed through the complex world of Pythagorean thought, from the enigmatic figure of Pythagoras himself through mathematical discoveries, cosmological speculations, ethical practices, political disasters, and lasting influence on Western civilization. What emerges is not a simple narrative of ancient wisdom or primitive error, but a nuanced story of human beings grappling with fundamental questions about reality, knowledge, and how to live. The Pythagoreans were simultaneously brilliant and misguided, pioneering and dogmatic, inspiring and dangerous. Their core insight that mathematical relationships reveal deep truths about nature has been vindicated beyond anything they could have imagined. Modern physics, chemistry, biology, and technology all depend on mathematical description of natural phenomena. In this sense, we live in a Pythagorean world, one where numbers govern everything from subatomic particles to galactic clusters. Yet we have also learned to separate legitimate mathematical science from numerical mysticism, to value empirical testing alongside theoretical elegance, and to recognize that mathematical description does not necessarily mean mathematical substance. These lessons came partly from Pythagorean failures, teaching us what not to do as much as what to do. The questions Pythagoras raised remain alive today. Is mathematics discovered or invented? Why is the universe mathematically describable? Should beauty guide our search for truth? How should knowledge relate to ethics? What qualifies someone to exercise authority over others? These are not merely historical curiosities, but urgent contemporary problems that physics, philosophy, and politics continue wrestling with. In engaging these questions, we participate in a conversation Pythagoras began, one that will likely continue as long as humans wonder about the nature of reality and their place within it. Perhaps the deepest Pythagorean legacy is simply this: the conviction that reality is intelligible, that pattern and order exist beneath apparent chaos, that human reason can grasp truths transcending immediate experience, and that living according to such truths matters profoundly. These beliefs are not self-evident, they could be wrong, but they have driven human intellectual and ethical development for millennia. Whether we call ourselves Pythagoreans or not, we inherit this faith in reason, order, and meaning, even as we argue about what it entails and whether it is ultimately justified.